This is a typical feedback delay network. You've got a number of delay lines in parallel, and I have to thank Elliot for this nice stick Z diagram. These delay lines each have their own T60 filter, so that's given by G over here. And then they are all connected to each other via this feedback matrix, which I call M. And this feedback matrix determines how strongly coupled these delay lines are. So if this is an identity matrix, then the delay lines are completely decoupled. But if it's not an identity matrix, then you can determine how strongly coupled the delay lines are by controlling this matrix. I show the transfer function of the FDN, and the only interesting bit here is this identity minus lambda of Z. So that is what is known as the characteristic polynomial, and this determines the system poles or the modes of the FDN. The problem with the FDN is that parameter tuning is still somewhat of an art, so it's not very easy to design an FDN that sounds good. And replicating a space exactly is quite tricky because you can design the B's and the C's here to sort of denote moving source and listener positions, but it's not trivial because this is not a physical model, it's not even a geometric model. So designing an FDN that sounds good is still quite difficult. So I'll be talking about the mixing matrix here because that is what my work looks at in detail. Now the mixing matrix needs to preserve energy in the system, and for that it can be unilossless. That's a set of matrices that can preserve energy in the system, but I particularly look at unitary matrices that have this nice property where if you take the Hermitian transpose and multiply with itself, it should give you an identity matrix. This matrix has eigenvalues on the unit circle with radius 1, with modulus 1. So the way I design this mixing matrix is that I start with 2D rotation matrix, which is parameterized by theta. And this is a simple structure. This matrix is unitary by design. Now if I take, but this is just a 2 by 2 matrix, but I might have an FDN which is 16 by 16. So if I want to extend the dimension of this matrix, then I can take the Kronecker product of the matrix itself a number of times. And that will give me a larger matrix. The good thing about the Kronecker product is that it preserves unitariness. So this resulting matrix M that comes from R is also unitary by design. And it's nicely parameterized by this angle theta. So if you've got theta equal to 0, then you have basically an identity matrix, which means that all of the delay lines are in parallel. There is no connection among them. Whereas if you have theta equal to pi by 4, then you've got plus minus 1 by square root of 2 in each of the elements, which means that these lines are maximally coupled with each other. Now this may represent how much furniture you have in a room. So if it's a very empty room, then maybe you can get by with an identity matrix. It will give you a very sparse room impulse response. But generally, people like designing dense room impulse responses. So for that, theta equal to pi by 4 is a nice choice. But you can actually vary theta from 0 to pi by 4. So this is the structure that we proposed, which extends the traditional feedback delay network and couples multiple FDNs together. And this structure has some properties which is very adequate for modeling coupled rooms. So we see here that there are 2 FDNs. So these bold lines here represent a bunch of delay lines together. And these 2 FDNs have different T60 filters associated with them. So that's G1 and G2. And this can represent the different T60s of 2 coupled rooms. It can also represent T60s from different materials in a room. So it can be designed to do whatever you want to. And then there is this block mixing matrix over there, which determines how these 2 FDNs are coupled with each other. So on the diagonal elements, that's M of 1, 1 and M of 2, 2, that's just how the delay lines within each FDN is connected to each other. Whereas the off-diagonal elements, which is more interesting, is how the 2 FDNs are connected to each other. So how the delay lines among the 2 FDNs are connected to each other. So they individually control inter and intra-group mixing. And this is the structure that we proposed in our DAFX paper that Elliot was a part of. So now this is the new transfer function of the grouped feedback delay network, and it looks very familiar to the normal FDN transfer function, except now you've got this block mixing matrix that you have to take care of. So this is the slide where I propose how you can design the mixing matrix to have meaningful coupling between two spaces. So if you have two FDNs, one FDN can represent one room and the other FDN can represent another room, and you design the T60 filters individually. Then you couple them together in a meaningful way so that you can control how much coupling there is between the two rooms. So in this case, I think I have an 8 delay line GFDN with 4 delay lines for each room or each FDN. Now I've placed the source in the smaller room and the listener in the larger room as shown in that picture. So again, you will have a fast early decay followed by a late slow decay. And the design of the mixing matrix is interesting because, like I said, you have to design the mixing matrix to preserve system stability, which means it has to be unitary. But now we've got all of these new parameters. Earlier, I only introduced one parameter theta, which controlled the mixing in one room. But now I have 3 parameters here, theta 1, theta 2, and phi. So theta 1 controls the amount of furniture in one room. Theta 2 is, again, furniture or how well diffused the room is. So you've got 2 thetas for the 2 rooms individually. And then you've got this phi, which I call the coupling angle, which controls how strongly coupled these 2 rooms are. So if you look at the structure of this matrix, if you have phi equals 0, then basically sign of phi vanishes. So again, you just have like m of theta 1 and m of theta 2, which means the rooms are completely decoupled. So that means if there's a door separating the 2 rooms, you just close the door. There is no coupling among them, assuming that there is no sound transmission. Again, if you increase phi slowly for a maximum value of pi by 4, these cosines and sines become equal. So now again, you've got maximum coupling between the 2 rooms. And this matrix is always unitary, regardless of the value of theta 1, theta 2, and phi. So in this plot, I show the effect of increasing the coupling from 0 to pi by 4. So coupling equals 1 indicates a coupling angle of pi by 4. And I also plot the 2 separate impulse responses and the coupled response in yellow, and the normalized echo densities, which is the rate of increase of the echo density. A usual complaint with FDN reverberators is that the echo density rises too slowly. So ideally, we want the echo density to rise as fast as possible to a value from 0 to 1. And we see that as we increase the coupling, then the echo density, the rise in the echo density increases. So that's desirable, but it's also indicative of more coupling among the 2 rooms, because sound mixes faster between the 2 rooms. And here I show a 2-stage decay plot, where you can see, again, I've increased the coupling from 0 to 1. And the turning point, which is where the two slopes meet, actually shifts towards the left, which means the early decay is shortened as I increase the coupling among the 2 rooms. So in a follow-up paper that was published this year, I actually took some measurements and tried fitting this GFDN structure to those measurements to see if it emulated the same behavior. So unfortunately, this was during the pandemic, which means I didn't have access to a lot of spaces. So I had to record this in my bedroom and my bathroom. So I have a bedroom coupled with a bathroom. And the bathroom has tiles in it, and it's quite reverberant. And there's a door that separates the 2 rooms. So I opened the door in varying intervals and took a number of measurements to indicate less coupling to maximum coupling. And first, I fit 2 individual FDNs to the 2 rooms. And I did that by fitting some T60 filters, use this warped-Roney method. It's not very important to understand how this works. And these are the 2, and I only fit the late field, so I don't care about the early reflections because the FDN can't model that accurately anyway. So this is what I measured in the bathroom. Hopefully that's not too loud. And this is what the FDN sounds like once I fit all the parameters. And this is the bedroom. So it's much shorter. And the FDN. So the bedroom doesn't sound exactly alike, but again, this is quite a difficult optimization problem. So I figured that it worked perceptually, so it was good enough for me. So one thing I haven't discussed so far is how do you place the source and the listener, because I mentioned that the source and the listener can be in the same room or can be in different rooms. So it turns out it's these coefficients, which is equal to these B's and the C's that determine relatively where the source and the listener are placed. So for example, if you set B1 to 0, then that means your input is only driving the second room. And suppose you you set C2 equal to 0, that means you only take the output from the first room. So that is equivalent to putting the source in the second room and the listener in the first room. So in that way, you can set some of these coefficients to 0 and control the relative positions of the source and the listener. So in these plots, first I place the speaker in the bedroom and the microphone in the bathroom. So that's the plot on the left that I'm talking about. And as I slowly opened the door between them and recorded the impulse responses, I observed a net decrease in the T60. And this makes sense because the bathroom is very reverberant, but as I'm coupling it with a less reverberant room, then the net T60 actually decreases. And the same behavior is observed in the GFDN when I placed the source in one room and the listener in the more reverberant room. So that's quite promising. Of course, these plots don't match exactly, but I think the net perceptual effect was good enough for me again. And in the second case, I placed both the source and the listener in the bedroom. So again, you have a bedroom coupled with a more reverberant bathroom, but in this time, both the source and the microphone are in the bedroom. And in this case, as you open the door connecting the bedroom to the bathroom, the net T60 actually increases, because you're coupling a less reverberant space with a more reverberant space. And again, the same behavior is observed in the GFDN when I placed both the source and the listener in the less reverberant room. So now this is what I'm working on currently, which is frequency-dependent coupling. So far, I have only discussed coupling matrices that are scalar. So, of course, they have parameters, the theta and the phase, but essentially there are no filters in the coupling matrices. And there are some advantage of putting filters in the mixing matrix that Sebastian Schlecht has shown. So if you put delay and use delay and filter feedback matrices in the FDN, it actually gives you a faster rise in the echo density. And this paper shows why and how. So there are some obvious advantages, but the other advantage is that if you want to model diffraction between the two rooms, because that is inevitable, since you have a door or an aperture that's connecting the two rooms, if you have low frequency waves that hit the edge of the door, they're going to bend and pass through, but that's not going to be the case for the high frequency waves. So there's an automatic low pass filtering that happens in coupled rooms, but the FDN structure I've proposed here cannot handle that. So I was looking at extending the FDN, the mixing matrix in the FDN, so that it can emulate wave effects such as diffraction and scattering. Now this brings in some new constraints into the design of the mixing matrix. So far I've said the mixing matrix needs to be unitary to preserve energy, but now it needs to be what we call para-unitary. So these are all polynomial matrices. That means the matrices can be represented as FIR filters, essentially. So if we were to write it as a function of Z, then this identity has to hold true. So if you take the inverse of it and then do the Hermitian transpose and multiply with itself, it has to be identity. So this is what is known as a para-unitary matrix, and this guarantees system stability. So the next question was, okay, I'm proposing a filter feedback matrix, but how do I design it in a meaningful way? So I worked with this mid-frequency diffraction model that I found in this paper, and I'm sure there are more diffraction models that can be exploited. But it basically gives you a tau, which is a transmission coefficient between the two rooms. That is a function of theta, which is the incident angle, so the angle of the sound, the incoming sound wave, and k, which is your wave number, which in turn depends on frequency. So this tau is a function of the frequency, as well as a, which is the radius of the aperture. So depending on what size the aperture of the connecting rooms are, this transmission coefficient is going to vary. So I took an average because I don't really know my theta in case of the FDN, but I can assume that after a number of reflections, the incoming sound waves are from all possible angles. So you just integrate tau from theta equals to 0 to pi by 2, and now what you get is an average transmission coefficient, which is only a function of the frequency, and actually also the aperture size. So you can assume there is a comma A over there. Now we have this frequency-dependent transmission, which we can design as a filter. So if theta were to go to pi by 2, so if the angle of incidence was absolutely normal, then this becomes a sinc function because sine of theta is 1. So you essentially have a sinc squared function, which is best approximated by a triangular window. And in blue over here is what I get from numerical integration, and I think in red is what I get if I just approximate the filter response with a triangular window. So if you choose the correct length of the triangular window, you can model this diffraction filter. And below is again the difference between the exact filter, which is given in the solid line, and the triangular window, which is given in the dashed lines. And we see that as we increase the size of the aperture, the length of this filter increases, and the value of tau also increases. So, of course, as you increase the aperture between the two rooms, then the transmission coefficient increases. Now, this is the structure of the mixing matrix that I propose, and it is para-unitary by design. So if we were to do the math over here, we see that the matrix times its Hermitian conjugate times itself will give us an identity matrix. And the problem here is that we have this off-diagonal term, which is alpha of minus omega. In the time domain, that translates to alpha of z inverse, which is a non-causal filter. So you cannot implement this in real time. If you do not have real-time constraints, this works beautifully and also sounds quite good. But assuming, let's not talk about real-time implementation now. You have this filter, which is a symmetric filter, and you can use that to construct this para-unitary matrix. So this is just a small example where I use the scalar coupling matrix, which I discussed before, versus the filter coupling matrix. And I increase the size of the aperture, and immediately you can see that the normalized echo density rises much faster. So that's a good thing. And this is what it sounds like. So this is with a very small aperture of, I think, 2 millimeters. So practically there would be not much sound going through, but if we were to normalize the impulse responses, this is with the scalar matrix. And this is with the filter matrix. So the low pass effect is quite prominent. And as you increase the aperture size, this is with an aperture of 5 meters, which is quite large. This is the scalar matrix. Sound diffuses much more quickly, so the T60 is much shorter. And this is the filter matrix. So again, the low pass effect can be heard. And these are just two stage decay plots. There's not much interesting going on here. So coming to real-time implementation, there are two problems. First of all, it's non-causal, which is the main problem. But secondly, you also have quite a large FIR filter if your aperture size is large. So it's maybe like 100 samples or so, which you can handle with real-time convolution, but still it's not ideal. So the next question I wanted to tackle was, how do I design a low-order para-unitary matrix so that I can implement it in real time in a plugin? So this is a little bit of math that's not too hard to understand. So this is a nice theorem which tells you that starting from any unitary matrix, you can actually construct a para-unitary matrix. So let's say you have a unitary matrix U, and the columns of that matrix are linearly independent. Now, if you were to take the outer product of each of those columns, you would have what they call an orthogonal set of idempotent matrices, so P1 to Pn. These set of matrices have some nice properties. That is, if you take the matrix Hermitian conjugate times itself, you get an identity matrix, so that Pi, that means Pi is unitary. But if you also take the inner product of any two matrices in the set, you will get 0. And turns out if you do the math here, then this particular matrix that I propose, U of Z, which is just written as a linear combination of these orthonormal set of idempotents, is paraunitary by design. And this also gives you some degree of freedom because you can choose the order of Z, so Z to the power Tk. You can choose a filter order as whatever filter order you want. And there is also that gamma over here, which is the weighting before each before the sum of each matrix. This gamma is typically a complex number, but as long as you ensure that its modulus is 1, then this matrix is paraunitary. Now it might seem quite esoteric, but turns out that we can use this to have a meaningful filter feedback matrix. So this is the coupling matrix that I had before, which is the scalar coupling matrix, cos of phi, sine of phi, minus sine of phi, and cos of phi again, and phi range from 0 to pi by 4. Now if I again take the column's inner product times, the column's outer product, sorry, you get these two matrices, P1 and P2. And now if I use the previous formula I mentioned before, I take P1 z to the power minus 1 plus e to the power j beta P2 z to the power minus 2. And these z's can be anything. It can be z to the power minus 3, minus 4, whatever you want. Then we have a paraunitary matrix. And we also have this parameter beta, which now can go from 0 to pi by 2, that can actually control the filter response of this matrix. So this is a pole 0 plot, this is a 0 plot. There are no poles here. It's an FIR filter. And these 4 plots are actually just the 4 elements of the paraunitary matrix. This is a 2 by 2 matrix. So I show this for different values of phi and beta, because you also have phi, which is a parameter that controls the amount of coupling, and you have beta, which now controls the filter response. So we see that phi just controls the radius of the zeros, and beta controls the pole angle, the zero angle rather. So that determines where the nulls in your response will lie. And this is the frequency response. So you see that on the diagonal elements, you basically have a flat response, which is desired because that is just controlling the mixing among the different delay line groups. What you really care about is the off-diagonal elements of this matrix. And when beta equals 0, that is just a simple high-pass filter. But that doesn't sound very good. So as you increase the value of beta from 0 to pi by 2, these are the different filters that you get with their zeros lying at different frequencies. So you can essentially design a low-pass filter and have the cutoff frequency in different positions just by using this one parameter beta. I think I have 5 minutes remaining. Okay. So I incorporated this into a plugin. So this is just a very simple, ugly-looking plugin that does stereo reverb. I'm considering doing a binaural implementation, but it's not immediately clear to me. And it just uses this eigen library, which is just a linear algebra library in C++, and it runs in real time. It takes about 8 to 9% of your CPU time, so you can run it with some other plugins. And I have these first-order shelf filters in each room, which controls the individual T60 response. So I'm going to try to play an example with and without the plugin. Let's see. Yes. So I recorded some guitar, and this is when the plugin is off. I turn it on. So, I mean, you can do some gain adjustments, but you can also determine the different source and the listener positions. So this is when both the source and the listener are in room 2. And if I place source in room 1, of is basically my parameter data that I can change. Coupling percentage is my parameter phi, which I can go from 0 to pi by 4. So this is when they're maximally coupled. And this is minimal coupling. You can change the T60s of the two rooms. And also the mixing of the two rooms. So there's lots of parameters to play around with, and I have not done a perceptual test yet, so I don't know how meaningful each of these are. But that's something maybe someone in this lab can do. Okay, so in summary, I've proposed the grouped feedback delay network and shown how it can be designed to model the acoustics in coupled rooms. And I also fit it to some measured data, and I saw that it actually works. It emulates the behavior correctly. And I also spoke about frequency-dependent coupling. I'm currently writing a paper on this, but I'm not done yet. In that paper, I'm also exploring how to model scattering. And that's sort of a slightly different problem. The filter design for that is a slightly different problem. So for stability, this feedback matrix has to be para-unitary. But the matrix that are proposed here, at least most para-unitary matrices, will be non-causal. So I've also shown a theorem that can be used to construct a causal para-unitary matrix starting from a unitary matrix, which I think is quite useful. Yeah, these are all the references, and I'm happy to take questions. Thank you.
I think I'll open it up to the floor because the 5 other questions I'll ask you later. Have any questions for those? Tom?
I think we have a lot of questions. So maybe I won't ask all of them here, but maybe for later. One of the questions I was asking myself, in the first paper you published at Defix about this topic, you claimed actually that you could easily implement it for an arbitrary number of rooms. How would you, for example, implement this type of structures with 3 rooms with the Kronecker multiplication operator?
Yes. Let me pull up this other paper. So in the appendix of the Audio Engineering Society journal paper, we actually showed some math which said that, okay, if you start with mixing matrices that are unitary in the first place, let's say for n coupled rooms. Can I use the whiteboard?
Yes, sure.
Yeah.
I think there's a pen.
Yes. So say you've got 3 rooms, R1, R2, R3. And you've got the mixing matrices m of theta 1, m of theta 2, and m of theta 3. Then you can construct a unitary matrix from this, and you've got different coupling coefficients, say phi 1 and phi 2. So if you were to form, and phi 3 as well, sorry, which is the coupling coefficient between room 1 and room 3. Now if you were to take these in a matrix, so just a matrix of coupling coefficients, as long as you ensure that this matrix is unitary by design, then you can create a resultant mixing matrix from this. And I'll just pull up the paper. So, we go down to the appendix. Yes. So this is what the resultant mixing matrix would look like. I haven't written it out, but it's a block mixing matrix, and your phi here is just a matrix of coupling coefficients. And turns out as long as phi is unitary by design, then the resultant matrix will also be unitary.
Yeah, I haven't read that, so maybe I should. I think I had another question as well. Did you consider the the case where you have an unsymmetric coupling coefficient, as it is, for example, in the Kramer-Müller theory, where actually he came on these geometric coupling factors. And how would you handle that in order to...
I think that question is harder to answer, because here the coupling matrix is symmetric by design. I would have to do the math to see if it still works. If it's not symmetric, so the coupling between room 1 and room 2 is not the same between room 2 and room 1. So that's an interesting question for me to answer. But I believe we are working on that, so let me know if you found anything.
I think actually if the matrix is unitary,
Yes.
there is this constraint of having this symmetric coupling coefficient. That's a couple of months ago, so I can't exactly remember. But I think this constraint, this unitary constraint, is not valid anymore. If you, yeah.
Mm-hmm.
I was really interested in your plugin, and I wanted to know, you talked about the incidence angle.
Mm-hmm.
Do you have anything that illustrates it in the GFDN plugin?
So in this plugin, I used the second implementation, which is just this two-tap filter, which is here, yeah. And in this case, I can't really control the incidence angle at all. The only parameter I do control is beta and phi. So it's just a very coarse approximation.
But still it makes sense. And the second question is, what do you call asymmetrical coupling? Like, it's one way it's like 70%, and the other way it's not 70 but less? Do you have a real case scenario? An illustration of a room where it's not...
Very simple. Okay, I will try not to go too much into detail, but if you like, for example, look at the Kramer-Müller chapter on the coupled volumes, actually, it defined what he calls the coupling factor or something, which is actually the ratio between the surface of the opening, so the coupling surface, over the coupling surface plus the equivalent absorption surface for each room. And so you can imagine basically that if you have a different coupling, equivalent coupling surface, equivalent absorption surface in each room, then you have by nature asymmetric coupling coefficient. And also another observation about that is also the frequency dependence of these coupling coefficients. Mm-hmm. So here you talked about the frequency dependent coupling factor because of the diffraction, mm-hmm. but I think there is also this frequency dependent coupling coefficients, which is due by the fact that you have also a different amount of absorption in each room along the frequency axis.
Right.
Yes.
It's been a while since I read that chapter, but I seem to recall they rewrite the entire problem in terms of kappa, which is the geometric mean between the two coefficients of the two rooms, so you end up having a symmetric problem. It seems to me, I haven't read it in a long time, but yeah.
Actually, it is still dependent on the two coupling coefficients.
Yeah, no, but it's just the mean. Like
the geometric mean is not sufficient for sorry. Yes, the geometric mean actually of the coupling coefficients is actually not sufficient for describing the entire model actually. So if you have if you look, for example, you choose a geometric mean for the coupling coefficients, and then you take another pair of coupling coefficients with the same geometric mean, you will have a completely different system, actually. Yeah.
Do you have any other questions? Aiden. Oh, Marcus went first.
No, I was just wondering if you've been thinking about an extension to three-dimensional room impulse responses and three-dimensional FDNs.
That's super interesting. That's something I do wish to work on, and I think Benoit is looking at that. I would be very interested in looking into that, but so far I have not.
Okay, I guess I don't want to ask too theoretical of a question. Of course, you've mostly just been using this, for fun, informal listening, that sort of stuff. those of us, I think, that have implemented or worked on FDNs, we know how challenging it is to come up with those magic delay lines. You know, there's a lot of, it's tough any way you put it. Would you say that with these structures that, is it helpful or hurtful in your, you know, your quest for, you know, whether you are looking for something that's smooth or something that has, you know, a good amount of buildup? Like, are these additional things that make it feel more physical also freeing, or does it make it more difficult to find something that sounds good?
Yeah, that's a very good question. I think there is, it gives you more options, like more degrees of freedom to play around with, because there are all of these parameters. But if you don't know how to use them, then it's difficult to design something that sounds good. So it really depends on the end user and how willing they are to sort of explore it. I think it's something that you also learn with time. As you use a plugin like this more and more, you figure out what the little things do. But I think this is where a perceptual test is very important, where you play around with the different parameters and you condense down to, okay, this parameter changes this, and this is what it sounds like. I think it is overall useful because you have now more degrees of freedom to play around with, so you can do more things with it.
I mean, I'm interested in how kind of the signal processing parameters that you have relate to physical parameters in a coupling space. So your coupling percentage, I mean, is if I actually have a coupled room and I start changing the coupling area, more things change than just, you know, the level at which the decay happens. The two independent decays start getting affected. And your coupling is a percentage, but a percentage of what? Because there actually isn't a normalized kind of concept in terms of coupling area. So I'm interested to know a bit more the meaning of those things and how physically based your approach is or could be, I guess.
Yeah, I think a fully physical model is far away from this. It's a lot more complicated. But this just gives you a very simple way to manipulate certain things. Like, for example, this plot over here that you're talking about. It's the first plot. Right, over here you essentially more or less just have this change in the turning point and not much else. But in reality, other things would also change. So instead of saying that, if I have said it, then I'm sorry about that, phi controls the size of the aperture, I would say it's a very gross approximation of the amount of coupling between the two rooms that controls this particular parameter. And turns out that it also changes the T60s slightly, but maybe in this figure you can't really see that.
But if I go to maximum coupling, to you, in your vision of what maximum coupling means, what happens at maximum coupling?
Yeah, the door would be like wide open.
Okay, so it should then function as a single space with a unitary, a single decay rate because it's a single space.
Even then, I think if the reverberation times the two spaces are significantly different, it would still show some kind of... Exactly.
Right, but it's a single slope.
Not in this case.
Right, so that's what I'm trying to understand.
Yes,
so I mean,
yes.
maximum, I mean, if I say the coupling between here and the hallway as a function of that door, I can have the maximum opening of the door. That doesn't mean the maximum, I could take the whole wall out.
Yeah.
So it's a percentage of what how are you normalizing this maximum concept of coupling?
So the reason why I capped this at phi equals pi by 4 is that is when stability is like, that is when it gives you an essentially Hadamard kind of coupling. So that's the most you can get out of an FDN. But that does not mean it's the most you can get out of the rooms in general. So it's just a mathematical constraint.
Have you tried to say couple your abstract coupling coefficients to a more physically based model, like having the Kramer-Müller model working as a means to assign the parameters that then follow, which could be a pretty, I mean, that's a relatively efficient way of doing the calculation, but keeps it physically grounded
physically more
in
meaningful.
a sense.
No, this is just a very rough approximation, and it kind of works, I think, in music because people don't care about.
It's more of an effect than.
Yes, it's more of an effect. Yes, okay. Absolutely.
Okay. Any other comments, questions?
Maybe it's a bit off topic because I'm not an expert in this subject. I just would like to know a bit about these kind of networks, or FDN networks. And I would like to know the aim or the ideas behind this kind of networks. So, for example, CNN were born for image recognition, and I just would like to know a bit more about this network. So, if you can help me.
Brief introduction.
No, just the ideas. So.
Yes, I think the paper that I cited here, although it's not the first paper on FDNs, but it is the paper that really picked up by Jean Magro. And it's just, the concept is that you have these different memory elements. These are what are called delay lines. And each of these delay lines has an associated filter, that's G1, G2. And overall, the net effect of this kind of a structure is to create this room impulse response in the time domain. So if it was just this direct path, then you have the input going in through D, which just controls the gain, and then you get the first spike over here. And after that, these early reflections are what's coming out of these delay lines. And you can adjust the length of these memory elements to space your early reflections out. So you can actually control where these spikes happen. And the filters, they control this decay rate, which is otherwise what I call the T60. So you can design these filters to get a particular T60. And as your input goes through the network, so if you just have an impulse as an input, this is what you get from the output. Then because of this mixing matrix, you get these, this late decay, this diffused field, which is after the network has finished mixing, then you get a lot more impulses out of the input. So that is when you get this late reverberation. So as time passes, the network will give you late reverberation after a certain point. And that's a very bad introduction, but you can read this paper, which explains it better.
One more thought?
I think it's not a question for Orchisama, but as I know Daniel a bit, and I think his PhD is about a completely different topic. The idea behind that is if you have a room response, basically, which we call the room impulse response, the idea you could also generate one and then use like real-time convolution algorithms in order to convolve your anechoic signal with this room response. But it's extremely costly. So the idea behind this kind of circuitry is actually to make it very computational cheap, and so that's the reason why this kind of circuits are well appreciated.
They did it because they had to.
Right. Yes.
If there's not any more questions, then I'd like to thank Orchisama again for coming one more time.